will, and then it will turn the thing into like a synchronous design, and then like why do we do the synchronous design, right? And then there's also the statics timing analysis STA, and then like it has summary. So, but when I look at that, the part of STA, how to explain like the timing and so on, is really very short. It's not much. So that means like after this portion, this chapter is I think one of the most important thing that you need to understand, because no matter what, when you do a design, you need to know like the timing. You need to do the STI to know that if your design meet the requirement or not. So that's the key thing. And if it doesn't meet the timing requirement, that means it doesn't meet the timing requirement. It's not only about the frequency, it's also meet the whole time, the whole check, which is like that one is that regardless you have, okay, there's two things, setup check and hold check. Setup check is to check if the design meet the frequency or not. Let's say we target 2 gigahertz, but because our data path is too long, then it's just like reach to 1.5 gigahertz, but it's still working. It's just a function, it just operate at a lower frequency. That's okay. The hold check is even more important, because at the hold check, if it didn't pass, the circuit won't function. If the circuit won't function, so the 2 gigahertz or 1.5 gigahertz doesn't matter. So that's why we have two things like that. We need to know, you need to know when we do the static timing analysis. But in this like a slide, when I look at that, I'm surprised that like it's very like short and nothing mentioned. So I guess after this, you don't know what to do with the SDI. You look at there, and then you know, and let's say like you have that, and you know what to do. I'm sure about that. So because of it, I will change that. Like I will go very fast, like skip very fast about the timing issue with the logic data. Why is the reason they go to the synchronous one, and I will focus on the SDA. So I think the first class, like the CC1, I just follow the framework here, and I realized that they missed a lot. So I think next class for the CC1, I have to like make up for that. So let's start with this one. Timing issue of the logic data, right? So this thing is like, let's say we have the circuit like this. The circuit like we have a simple one. Then we have you can see that the longest path is from A0 to B0, right? 4, 1, 1. So this one is the delay is a 6 unit. The short one, the shortest delay will be like A1 to B1. 1, 1, 1 is a 3. Okay. So now with this, so when let's just like they change like if the input change from 0 to 3, which is 0, 0 to 1, 1. Let's see like what is the change at the output B1 and B0, right? So okay, this thing I think regardless at the end it changes. You can take you can like look at the diagram here, the schematic here with the number delay number here, and then you can figure out this thing, right? This thing is like not much to explain. You can see that. I don't want to go in here. Then it's just like you can. I think you can figure it out. The thing is that after look, this one is the critical part, the longest path delay, which means that you expect that after 6 time unit, right, you will get this thing like ready correctly. So it's like from here 0, 1, 2, 3, 4, 5. No, actually shit. No, yeah. No, actually from here. 1, 2, 3, 4, 5, 6. Okay. After 6 time unit, the output is 2, which is a 1, 0. Right? 1, 0 is the correct value here. 1 and 0 here. So when you have 1 here, when it's 1, 1 and 1, then that means this one is 1. And this one is 1, it means this one is 0. So the correct value is 1, 0, which is a 2. So that means like if you have a A1 and A0 is like a stable like this, you have the value here is correct. Now they just like do like a change a little bit. Instead of keeping the A1 and A0 like a stable like at 1 and 1, they change it to like back to, it will change that to back to 0, right? A0 1, 0 to 1 and now change back to 0. But they change back to like with an only 3 unit. After 3 unit, you go down here, right? You get change that back to 0. And then let's see like, so the expectation is when you go back to 0, 0, okay, what is the value of when the input is 0, 0, right? What is the output supposed to be? If 0, 0, the output supposed to be 0 here, so it's supposed to be 0 here. 0 here is supposed to be 1 here, so the output supposed to be 0, 1. So that means we're supposed to get the output is a 1, right? So now we can see that like this after 6 unit, 1, 2, 3, 4, 5, 6. So this one is a 6 unit. The output is a 0, which is wrong, right? It need to get 3 more, but it didn't get anything. Let's see. No, this one A and B. Yeah, at B here. So it's supposed to be 1 here. So for A equal to 3. Oh, okay, sorry. I think it's after that it would correct here. But okay, the question is when we have a 3 here, we have the input is a 3, the output supposed to be 1, 0. But we see that it's a 0 or 1. We don't have anything is like any value of 2. 1, 0 mean 2, which is the output, the input here cannot be transferred to the output, right? So there's something wrong here. Yeah, there's a circuit here. So you can look at that and you can like check in and you see that there's a no value go out as 2. So that means like the circuit doesn't function correctly. Why? The reason is like we have a this one, we have a certain like when you have the input can change anytime. You see that the input can change like here after 3 unit, after 4 or 5 unit, it can change like anytime. With that, it has a certain like it need to have a certain rule, or a certain like we need to have the maximum delay minus the minimum delay. That means like the input need to be stable with at least for that, right? 6 is a 6 maximum, minimum is 3. So that means the input need to be stable for at least more than 3, which is a 4. At 3, so that like the input can be conveyed to the output. So in this case, the 3, it doesn't work, right? Now if you like increase like the time for 5, see? Input now like a change like stable for 5 unit, then you can see that like the output happen like 2, right? The output like appear here 2 corresponding to input 3 here. What does it say? What does it mean? It means that like with those kind of circuit without this like the input can change anytime like this, we have the risk that like we have to maintain like the input need to be stable for a certain amount of time so that the output will be like reflecting the input. But if you look at that, right, so how can you get the output? You have an output here, but how can you use this output, right? So how can you use this output? You have no, and then 2, it changes to 0, it changes to 1 here. So how, and then you can see that 2 here is for 2 time unit, 0 here is for 3 time unit, and 1 here is that. So how can you know where, and sorry, how can you know when to get the output data out to use it? You have to have some kind of the time unit here. What is the reference to, right? It changed here, so everything is changed here. Let's say it changed here, and then like it, instead of changing the 5 unit like cleanly like that, it changed to 4.5, 4.6, and so on. So everything it's just like you don't have any idea when it changed. the input data here can be like a transfer to the output correctly, but you have no way to recognize that. It's very difficult. You need to some like a handshake thing, which make it complicated. So because of it, this one. So longest delay time needed to correct the output for the correct output to appear at the output. Okay, shortest. Yes. So okay, I just went to like go fast. Those doesn't need to be. So the thing is now to avoid that thing, they will put like the flop at the beginning, so that like now you have a flop, you have the clock. So the data change only when you have the rising edge of the clock, right? So for that you have that means that you can go back here. That means like the here, right? So the time is not change up to 3 or 4 or 5. It will change the value only after the clock period. If you have, let's say if you have the here, go back to here. Sorry, I think okay, we remember we have the part here from here to here is the critical part, which is like 6 time unit, right? So you will define the clock period as 6 period. Then that means that only the things here can change whatever it was. However, the output here, which is the input of this circuit, can change only at every rising edge of the period. So that means that it can change that if you define this one is like a 6 time unit, then you accept, right? So that's why I think when you introduce the flop, I think you just like eliminate the problem of like the data need to be stable within a certain like amount of time, and they will like put that together. When you have clock, one here, one here, one here, one here, that's okay. Now if we have the clock, it didn't mean like they have the same clock. But if we don't use the same clock, we'll have even more trouble, right? Now look at that, we have clock 1 and clock 2. The clock 1 and clock 3, because it's no relationship between them, which is we have it can be anywhere. The phase relationship can be 0 to like a 180 degree. Even like these two clocks are the same frequency, right? It will move around. So you don't know like the delta here. The T0 here is really like T0 here is unknown because it can change over time. It can like it depends on the circuit. So the T0 here is like really unpredictable. Because it is unpredictable, so you have a T1. It need to be like a T1 here, and then you have T2 here. So it's really like is this data when it's ready here, it can be like you see that is this one a T1, right? When it's ready here, it's ready here, and this one going here. It will be like it will mess up our data going forward. I think okay, you can like think about this clock 1 and clock 2 as these two, because they have no relationship with each other. Even they have the same frequency, we can consider that they are like asynchronous. When you have asynchronous, we have a trouble to get the data like correct to this one. So the bottom line is like they will have to do the synchronous design. It means that you have only one clock for all the logic. So when you have all the clock, so everything it just happen like within the clock period. For P1, for P2, right? This one, when it happen here, it's ready after a period, it happened here, right before the next edge. So the next edge, it will go to this one. So the data here is ready and go to this one, and the third one go to this one. So with that's why like we have this one will solve any problem regarding the stable data or like the asynchronous design here, because you don't know the phase. This one, if it happened like this one, right, it just happened right here. So that means that the thing is the T1 here, you go from here to here, and T2 here, you can see that this for that to work, right? So the T2 here must be bigger than the, right, must be bigger than the T1 here. Actually, T2 here is here. I think the okay, let me restate the period of this one, the T2 need to be bigger than this one because of this phase relationship. So it need to be bigger, which is you have a different clock here. Clock 1 will be different from clock 2. You cannot have it as you cannot have it the same frequency, which is how can you produce a two clock in the like a multiple clock in the circuit. Usually we have to maintain one clock so that like easy to easy to control it. If you have imagine that you have a 10 clock, right, for the same block, 10 clocks for the same block. So imagine what is the source of it. So how do you control it? It's very complicated. So that's why we need to get into like only one clock. So those things is kind of like you understand that, but those things is like you might not even like yeah, it doesn't matter. Those things is really like a kind of waste of time. That so now I think most of 90%, 90 to 95% of the design right nowadays is a synchronous design, which uses one clock for all the logic block. This one is I think the statement here is not completely correct, because in a block, in a design, there will be multiple clock, not just one. But the main block, which is like okay, when you hear like the Intel, right, Intel processor like working at 4 gigahertz, right, it's not every single cells in every single flop in the design operating at 4 gigahertz. Only the core, only the main circuits operating at 4 gigahertz. But when it goes to like it has to go to the memory, it has to go to the IO, it has to go somewhere else, then the frequency will be much lower, which is they have a multiple clock. And when it go from like the inside, it go outside, like when it go to the DMA and then go to the graphic card, the bus, the bus clock will be like much lower, because you cannot afford to have a 4 gigahertz bus on the PCB, right? So which is like it's like the synchronous design basically is for each block. It's not like for all the logic block. For each block, it will use a one clock for, it's supposed to be for each logic block, not all the logic block. So that means because between this block to the other block, it could be different voltage, could be different frequency. Why? Because like let's say like a block of you have a block of processing the image. One block is processing the let's say the display of the graphic, right? So the two doesn't need to be like the same frequency. So one is operating, let's say like handle the video game. It need to like it need to handle the very high throughput. So it need to be very high frequency. The other block is in the processing like the image. So it's a static. So it need to process as much as possible, but it doesn't need to be like as critical as the graphic unit. So because of it, these two blocks will use different frequency, right? So which means like so the point here is that the frequency or the clock in design is not one. Even the synchronous, but it's not. There's never one clock. There will be like a multiple clock, but the main clock usually they marketing they will like they will introduce that as the highest clock, because highest clock make more impress, right? It's more impressive than the lower clock. Okay, so I think with that we have this one, right? Then now I think there's a three time of like a way of using the clock in the synchronous design. One, you have that is all rising-edge, so all clock is like, so that means that the data path need to be delay need to be like at most the clock period from here to here. The second one is a single phase clock. So they use every edge to like a trigger, right? To change the data. So so that means you see that the flop here with the rising edge, that's I guess the simple, you know what it is. And here it means that with the circle here, it means the falling edge. So the thing here, when you look at the picture here, oh, it looks nice. So why don't they use it? So they cannot use it because the time, like here when they set a, like a window, the when is the portion when the clock is 1 will be different when it's 0. So sometimes they call that like the duty cycle, right? This is some like attribute or like parameters of the clock defined as duty cycle, which is the ratio between the time when the clock stay at 1 and divide by the period. Ideally, the duty cycle is a 50%. That's what like the ideal clock. But real life is not, because of thing here and there. It can be like only 40%, 50%, or sometimes it will be like 70%, because you see that, right? The clock, if when it go through the inverter, it swap, right? It swap the status 0 to 1 and 1 to 0. So that means that in one like in one node, it might be the duty cycle might be 40%, but the next cycle, sorry, the next the next stage, it will become 60 and 40%. So which is like because of it, it depends on like it's really like a mess up the timing data. So the half cycle transfer here is a very limited use, very limited, and whoever design it need to be aware of that, and need to be aware very well, need to know very well what they are doing. Like because of the designer, actually the RTO designer, when they do that, usually they write it in Verilog code, which is has nothing to do with the real circuit. They don't even know how it's transferred to. Because I think it's not as simple like oh, you write the AND gate and NOR gate. What it's trying to like describe for the RTO code is the function. So it's quite a pseudocode, or like something like you have a plus b, or like a multiplied by. If you have a c equal to a multiplied by b, that's a multiplier. The multiplier is a big macro, right? In that, they will have like a lot of adder, shifter, and so on to like realize the function of multiplication. So the bottom line is like the guys who design when write the RTL, it he doesn't know much about the real life of the flop like that. So if somebody like want to use this half cycle transfer here, they need to be very careful. They need to know a lot of things about like this thing. Two-phase clock. So with that, right? So clock 1, clock 2, that use this one is like this one is you have like you have a clock 1. The clock 2 is the inverse of the clock 1, right? So inverse of clock 1, so that they do like I think it become like the same thing as this one. So these two, number 2 and number 3, rarely used, and so it's rarely used. I think this one is the one that try to explain what is the when we check the setup time and when we will check the whole time. So this one is a very simple one, which is you have the period. See, clock period is from like the launching edge here until the capture edge here, rising to rising. This one is the total cycle, one cycle. So the check will be simply to explain like they said the setup check will be like T2 plus setup time. T2 is the time from here to here, right? Or from here to here, and plus the setup time will be need to be like less than the cycle, so that like you see that it go from here to here is is cycle minus T2, right? So that the portion here will be the setup time, so that when the clock log in, you get the data out here correctly. If imagine that this one is a bigger than like this one, like the cycle minus T2 minus setup, sorry, cycle minus setup, then after setup time, it will be like too late. The clock here cannot like launch the data into this flop 2. But this one, the picture here is a very simple picture. It doesn't like tell much about really what we do in the STA. That's why then, so those things, I think now I want to like skip that quickly. STA is carried out several times by using various levels and so on. So the from RTL go to the route and post route, we have it go through synthesis, placement, CTS, and then route and post route. All these steps, after each step, we need to do the STA to see if the timing is like the timing met our requirement. So after synthesis, you run STA at the level like in this, we don't know where the cells really sit, where they're like not much, and then from here we just do like something like the gas, right? Use a white load model, or use some like parameter like a statistic model to calculate the Y delay. After the placement, we know where the cells place. Then we will calculate the Y delay by using like the Manhattan distance, right? If let's say like if two cells from here and to here, we just use the Manhattan distance like this, and then estimate the Y, and then like we have a Y delay. It is not correct. It's not completely correct, because when you have the length is correct, but what we don't know is what is the width of this one, right? And what is the layer of that? So the layer you don't know, so that means that because the resistance is different from layer to layer, the capacitance is different. So the only thing you know after placement is only like the length. So that means like we still have like the accuracy is still like not that high. It's better than this, but it's not that high. Now we go that, but this one at this step placement, we have a no clock tree. When you have a no clock tree, you have to assume that clock tree is at 0. Like the delay is clock latency is 0, so that like you can calculate the timing. Then after CTS, which is the clock tree, now is built. When the clock tree is built, now you know the clock go from here to here. See, you see that the clock in the picture here, it assumes that like here the clock here is 0 and 0, right? So you see that it's kind of assume that like clock at this point and this point is the same and 0. That's the assumption for the placement stage. But we cannot like in the real life, you have the clock come to here and the clock come here. It might be like the difference between the arrival timing arrival is about like it might be like in 100 picosecond or 200 picosecond, or if it didn't move well, it might be like nanosecond. So for the frequency, let's say 100 picosecond, you might think that, oh, it's not big deal. But remember, for the 2 gigahertz, its period is only 500 picosecond. If the difference between the clock skew between here is 100 picosecond, it will eat into this like a data part 100 picosecond. So this one, let's say like this one going here, the skew between the two is 100 picosecond, right? Let's say arrival here is 2 nanosecond. Arrival here is 1.9 nanosecond, right? So which is like this one is arrival earlier, which is it eat into the data part here 100 picosecond. So instead of, let's say for 2 gigahertz, instead of having like a 500 picosecond completely here, now you have to give that 100 picosecond for like the clock skew here. That means that the data part here need to be sped up to like, instead of 500 picosecond, it need to sped up to like only 400 picosecond, which is 20%. So byte alone. That's why I think. But at the CTS here, we have that. Then we can like assume we can have that picture. Oh, now I have that like 100 picoseconds different. Then I have to like optimize this one instead of to 500 picosecond. I have to optimize that to 400 picosecond. So that's a one level of accuracy improve. The next one after that, now you route the thing and you do the post route to optimize it. Then after this, you have the complete design, which is now all the part here, all the data part here is routed. All the this here is routed and everything is completely. Then at that time, the timing is correct. So the accuracy like go like increase from this to this to this because the data is missing, right? At this step, you don't have any like information, the data about the location of the cells. Here you have it, but you don't have routing information. You don't have the clock latency. Here you have it, but you still don't have the data about the routing. So everything when you have that. So but you cannot wait until the end to do the SDA, because if you do like wait till the end, it means that in the middle of thing here, you do something wrong. You went till here, you know how long the cycle, like the work cycle here, the cycle time from the synthesis go until like push round here. If everything is done correctly, it takes about a week. You cannot like offer to wait for a week to find out that, oh, I did something wrong in the place. You have to control, monitor that to see like, oh, after placement, that is wrong. So I have to go back and then like tune it up and go to synthesis, redo it, or I go to RTL to like to adjust it. So that's why I think the SDA will be like do that. This then, okay, I think multi-cycle part, if you don't make that, you just add into like you add the flop in the middle, it's called retiming. And then so that like the period now is divided instead of one, let's say like the total part is a 1.5 nanosecond, right? And now the target is a 500 picosecond because the frequency is a 2 gigahertz. So this one's a 1.5, it cannot meet. So we have to insert the flop here so that you have each of them will be only 500 picosecond. It's called the process of coordinate. This one called like a retiming. And another one is you have a handshake here, and then for the asynchronous, which is I think if you guys I think you when you learned about, I think you guys have the class of microprocessor technique or engineering something, and it will explain this thing. If you don't, I think please let me know. Now, okay, let's say I think there's some question here. What is that? No, okay, no question. All right, now this one is like when we have the same thing, clock 1 and clock 2, they are different, right? Clock 1 and clock 2, they are different. So that means like they will use the synchronizer which is they will use the synchronizer which is composed of 2 flops connected this way, no logic in between and either here. So this one is called like synchronizer. And how does it work? I think this one, this one is complicated. I will give you, I think we'll present another one. Is simpler to understand. All right. So on the right is the 2 flop connect together, and then we have that is the synchronizer, and on the left is clock A, on the right is clock B. So this clock A B is, you can see that it's they are like asynchronous, right? Nothing to do with. Now when you have the data, the signal come in, right? Is that here, this one. Okay. Okay. Yeah. Uh, so because you see that this one and this one, it happened like a meta when the meta yeah, the meta stable thing static happen, stability happen, then you have this one and the output will be like fluctuating, right? In theory, in theory, we never know when it will settle down, because in theory it means like when you have a one case happen, it means that it happens. But the difference between the practicality and the theory is that for the practicality, when the number like when it happened, but it happened in a very like a long time, we can consider as no zero, as nothing, right? Let's say like it happened one in a 1 trillion time, then we can consider that as like a nothing. It depends on our requirement for the reliability, for the integrity. So which is you guys, if you remember about like the class statistic and probability, for all the nature distribution, right? We have the thing like a distribution like this. Oh, you have like the bell curve, right? The bell curve. So with that, the 3 sigma is usually that distribution. So anything like happen outside of the 3 sigma, we can ignore it. However, this is more important because it's a flop. If it fail, everything's fail. So usually they will use like for the flop, they will use the 5 sigma or 6 sigma. In the old days, it's the 6 sigma, but now they use only 5 sigma. The reason is like the number of cells is too high. So if you use the 6 sigma, there's too many things. It's too many like data to use to collect. So at the bottom line, by the way, come back here. When is the meta thing, right, happen, then but usually it happen only like for a certain time and will get to stable. When I get to stable, this one you can see that it get to stable, and then the next clock will get to correctly at that correctly, right? The first clock will get that like this, and during this time the circuit will function like abnormally, right? So we don't want it. So the reason for the second one is just like to like time that at the second clock. So it will be delayed by one more clock. That's all. So the thing is that when the question that I think you guys fail is like the meta stability, right? It happened when this one is hand, and then it will happen. It can stay the undetermined time, or like an unpredictable time. Is more correct to say that it's unpredictable time, because it can be like it can settle down in any time, or it might not settle down. But the probability for that to not settle down is very low, that we can ignore. So that's why we have this picture, because usually when you have a meta stability happen, it means that this one might be go like forever. That's the theory. When we accept there's a certain amount of like a failure happen, like the yield, then most of the time it will happen like this. For 1 or 2 case out of like trillion, 1,000 trillion, it will be like a not settle down. But for this thing, I think when the circuit fail like that, I think the foundry or the chip maker, they are willing to like just like replace it. So that's why you see that like in here in Vietnam, right? If like the card has the bug or like not function and get back to like the seller, they will try to fix it and so on. Here they don't do it because the cost of fixing it is too high. They just okay, give me that, I will replace you another thing. That's it. That's because considering like the cost to fix it is more than the cost of just replacing the IC, the chip. Okay, so I go back to the class. Yeah, I think implementation those in. Okay, I think this thing, I think you can like look at that. Now I think we take a break, and then and then I will like present something like the timing part, how to read and understand what is the timing part. Okay, now we take a 10 minutes break.
Dạ thầy Việt ơi,
Yes.
Thầy lóc vô keo đúng không thầy?
Mm-hmm.
Để em chỉ cái lóc vô cái password.
Chỗ password. Ok, mình đang ở BK. Ok,
Bây giờ thầy
BK.
phải lóc ra lúc mà ở cái trang đầu tiên thầy nhấn chữ đăng nhập đó thầy.
Rồi bây giờ log out ra phải không? Ok, let me
Dạ,
log out. Ok. Thoát ra. Alright. Ok, bị đăng nhập.
Dạ, đăng nhập.
Rồi, cán bộ sinh viên.
Ở phía dưới nó có chữ thay đổi mật khẩu thầy.
Change password. Ok, yeah.
Tại vì cái này nó hệ thống quản lý tập trung, xác thực tập trung, cho nên là nó phải thay bên ngoài này chứ không phải bên trong.
Ok.
Dạ.
Nhưng mà bây giờ
Bên trong
mình phải nhập
thầy nhấn
cái
thử lên.
username trước.
Dạ, thầy nhấn chưa rồi?
Okay, let me do that. Change password.
Dạ.
Okay. Okay, I see it. Okay, I will do that. Yeah, do that later. Yeah. Okay. Let's do that now. Okay. Yeah. All right. Okay.
Được chưa thầy? This is okay.
Let me do that. Rồi mình làm xong rồi, nhưng mà bây giờ mình phải login coi thử. Come on. Okay. All right. I think it's working. Yeah. Rồi, được rồi.
Dạ.
Ok, cảm ơn Thịnh. Yeah.
Dạ.
Yeah. Okay, let me. All right. I think I have to have dinner right now, and then I will be back. Okay. Today is a little bit like yeah. All right. Okay, I'll be back like maybe like in 10 minutes now. Well, no dinner, so I think we can get back. Till now, that's why I said that at the metastability happen at the second position. Yeah, but the third one, that's what it get to. When it happen from that time to infinite. No, it's not like finite. When it happen, it can like get back to. It can get back to. It can get back to the correct value. It's just like when we said that like the metastability like happen and then it is taken to finite. That's just only a scope like certain cases. That's why. But that's why we like don't want that to happen, right? But the number again, I think that is for the probability for that to happen. The probability of that is only like for that to be like infinite. It would be like the probability for that is only a 1/trillion cases, and we consider that as a zero, right? So your question is like I think when we talk about meta stability, we talk about it cannot get into infinite. The case of infinite here is only a very rare case. But again, I talk about like the theory and practicality, right? Theory, that's correct. Practicality is not. So in the design, in the engineering, we talk about practicality, about the real life. That's why it can get back to, but still, even it get back to, you can see that here, even it can get back to, do you see? Yeah, even you can get back to this one, right? That means like at least this portion is unstable. So that means the data during that thing is not like usable. So you need to have another one to get like this one is data to correct this one. Which is the third clock. So does that answer your question? All right. So remember what I said is that theory, that is correct. Practicality is not. Even like, and then it makes sense that you have like it depends on the probability. That's why I think in the because in real life there's a nothing ideal, right? Nothing is ideal. Even you have the clock, you said that like the clock is 50%, but never is a 50%. And then like you never have anything like absolute in the real life, including social life or like including like a physical like a thing, everything, right? So it's just like that's why I think in real life we have to make things make sense in the scenario we are considering, which is in this case the probability we make is like a 1/trillion cases, which is reasonable. In the other case, let's say like as I said, like for the table, let's say you measure the table length and width. You say that the table is measured by 1 meter and 0.00001 thin. Oh, okay. That one. Let's get that. Get that one. You have to get back to like the picture of the flop, right? In the flop, you have the pass gate, and you have that like and after that transmission gate, and then the other one is the loop of the two inverter, right? Two inverter go in back loop, so that to state to stabilize the value. So that one, when you have this, then it can get back to the correct state. But I think that let's take, I will take that like I will take that offline. So if you want, I think just look at that and then you will see. Okay. All right. So now I think let me I think try to make. Yeah. Okay. This one. This is the please. Okay. Yeah. All right. Okay. Yeah. Oh, this one is. Yes. Yeah. Okay, here's the picture of like it describes the timing part in a circuit. So I think basically it's in general. So all kind of part, the timing part that we have in the design, it will be like that. This one is from the input port, like from like the pin, right? The pin like whatever from the external, and go to the logic and go to the, or like it, this one come from another block, and then go here and you go to like a logic and go to the D pin. The clock go like that, and then like this one is the part in between the two flop. And you have a when it's here, you go out and you go to the another block or go to the pin. So which is you can consider that each one is a block. Go in, you have a go like so that means, and then you have like this one go from the other block and go through the logic here and go out, so without any flop. So these are four. You have a four time of data part here is the typical of a timing report. I will present that later. But remember this one. So this one, okay, consider this, right? Consider this as your block, and all the timing part will fall into like one of the four part here. The first one go from the input of the block without the flop, go to here. And then this one, even like I draw, is the picture here show only the one part here, right? But this one is kind of like a representative of all parts between the, because between two flop you have 1,000 of flops, so you have 1,000 of part like that. So this one is the part from flop to flop. And the next one go to the like from here and go out. So that's a call like this one input part, and this one the output part. This one is a register to register part, and this one the I/O part. Go in input and output, and without any flop, call this one's the I/O part. So this to present to you like so now you understand like what timing part we talk about. The next one will be here, the capture clock and the launching clock. So you see that, right? So you see that this one is flop, right? So the part is between the flop to flop. So this one is in the data part go from here to here. Data part is defined as the part go from the clock input of the flop, go to the queue, CK to queue, and from here it go to the logic, and it end at the input pin of the flop of the next one. So you see that like this one can be called like for the data part from here to here, we can say that like this one is a launching, right? Launching, which is a starting. They call that this one is a launching flop. And this one, because it like ended and they capture the data into here, they call that this one the capture flop. Accordingly, you have the clock will be like a launch clock, and then you have a capture clock. The launch clock go to the launcher flop, and the capture clock will go to the capture flop, right? So you can see that here, and you have the common point here, and when you have the clock path go from here to here and go from here to here, so that will be the common point that like it use the same logic, but from here, because these two flop like a sit maybe one here, they cannot use it all the logic the same, so they have to use only a certain part of the same, and then like when it branch to this one, it branch to this one, so you have two things different because of these two like the different here, right? So here whatever it is here, the clock here, this part, right? If the delay of this flop, the cell change, they all change together for this, right? So let's say like if you have this, if you have like this that the same, and this one here go all the way to here instead of this thing, right? Then whatever this one, we don't care because whatever is changed here is still the same for these two, right? The key thing is the relationship between these two clocks. And the difference between the two clocks here is determined by these two cells and these two cells. In the picture, it shows you like the number of cells, like the part from like the launching part has a 4 cell, right? And the capture is a 4 cell too. However, in the real life, you cannot like let's say like this one is the flop sit right here, so it go directly to here. You have no like additional buffer. This one will go far away, so it go into here, it take like 4. So the difference between the two is like a 4 cell, right? So we will have a skill of that. Then the CTS, that means that the clock tree synthesis will have to try to balance that in the logic wise first. So which is if it has only like if it sits right here, then it will add even like there's no need to buffer it because it's the flop sits right here. But because the part go from here to the next flop here, right? It has a let's say in this case a 2. Then it has to add 2, like a loop 2 thing here, two cell here, so that like the number of cell go to the flop will be equal. That's first. The second is not because you have here you have only also like a Y delay. This one, if you just do 2 cell here, so there's no Y delay, then this part still shorter than this one, right? So that means that when they insert that, it will insert like the way that it add like a 1 in here and 1 go out here and it go back, so that like it balance not only cell stage but also balance with the Y length. That's like a now this are talking about the clock gating part. This one is they getting that, right? So this clock here, instead of going to like the flop, it has the OR gate here, and then like so this one's allowed or not. If you have this one is a 1, no 0 here, you have a 1 here. This one is for the OR gate, 1 block this gate, so there's a no like a clock come to here, right? When you have a no clock go to the flop, it means that this flop doesn't switch. If it doesn't switch, it means there is no switching power. That's how it controls the power, switching power. So you stop this clock coming in, that means this one doesn't switch, have no power consuming. But if this one like it doesn't switch, which means that this one doesn't work, right? That it doesn't work, but in purpose, because in like where they block here, it doesn't work because it doesn't need to, right? It's different from like you don't have a clock, you have a clock going here, but because of some stuck cat or some like a failure that it doesn't work, that's different. This one is a stop the flop operating in purpose. So in purpose, so that like no switching, no power, that's how they reduce the power. So this one is, so that means you can see that the clock part right here is not only like a go straight into the clock, but it will go through like some like clock gate. Then this is the asynchronous part. The asynchronous part go into the preset and clear. So for this thing, because it's asynchronous, usually you don't have any flop along the way. So it's like a reset usually. Actually, reset here, you go like so it's swap and go to preset. But this reset can go directly this way. because it reset, go to clear, right? So it will reset at the beginning or like a preset when it's needed. This with this one. I can repeat. Okay, that's it. So that's like explain the data part. That's data part. Now let's look at a real part, a real timing part. Let me see, where's that? Yeah, this one. There. Okay, I think. Can you see that? I think it's kind of small. Okay. If I do that, then, but I think this one is the typical timing part. Can you see this? Okay, good. So you look at that. Okay, the thing is, you see that like in the report here, this one is for, let me see. This one is let me see, this one I show like this. This one is setup part. Okay, this one is setup part. So the setup part, you have the starting point, right? It's the starting here. Oops. You have the starting point here. And then, okay, let me, no, how can I remove this one? Okay, so it show like a start point, which is like a certain, like you see that is a QREX 0, right? The starting point is a QREX 0 here, which is, this one is the flop, the launching flop. And this one is the endpoint, which is the M1. You have this one is the memory. It ends at the memory. Last common pin here, this one is the common pin that I show in the clock part, right? That's the common pin in the clock part. Part group, part time, max is the max means the setup, min check the whole time. Now you see that it's from the beginning. Here it starts from the clock, right? It's a 0 here. And then when it go to the first line here, you see that it will go to like 0, and then like the transition here, which is this one is the transition time of the signal. Then I think after that, I just like cut it here. It's too short. There's a 3 dot here, means there's a lot in here, but I don't need to like because I want to like to show just the part. So let's say like for this one go to the A and Z, and then the net here, right? This one the net. So A, arrival time, the part here, you see arrival time is 190 picosecond. After the inverter, it become 205. So you have this is increased by 16. That's the delay of the cell. Now you have it go to the A here, right? The A here. So the 7 picosecond here. Oh, you cannot see my because. Oh, okay. Oh, here you can see from here, right? Sorry. Let me restart. The cursor. Okay. I mean, I think I have to. Man, this should. Let me. Oh, okay. I think I can do this way. All right. Then like this. All right. Can you see my? Can you see my cursor now? This one, I guess you can see my cursor, right? Let's see here. All right. Okay. Yeah, here. Okay, so I think this one, let me repeat. This one is a 190. 190 is the arrival time here. The 13 because okay. Let's and 205 here 16 picosecond here, sorry, 16 picosecond here is the delay cell, the delay of this inverter. So because of that, you add into, you have 1205. The difference is 1 picosecond because of the significant digit number, right? So maybe 190 something here, add 16 here. No, 190 here, maybe 189.5.6, but it rounded up to 190. So when it ended up, you have a 205 instead of 206. Doesn't matter. Now the next one here, you have a 3 dot here. It means 3 dot here means I have quite a few thing, quite a few like a cell here, but I just cut it short, so we don't need to like get confused with that. So this one you have the A to NZ, right? So A here at the beginning you have a 7 picosecond here. So this one is the Y delay. The number appear at the A here, it means a Y delay. Appear at NZ is the cell delay because it's just like the delay at the end, right? At the end of input is a Y delay. Delay at the end of the output is a cell delay. So keep going like that. You see that. So from here, I said the clock out from the POL. You see POL here, clock out. And now I go that, you see that. And now I go to the clock in here. This one, oh, okay. Yeah, that's good. So this one, oops. Oh man. Yeah, okay. There you go. Okay, this one is clock gate that I talked to you, right? So you go through that in the clock gate, and after the clock gate, you see that you go to the flop. This one SDF, the DF here is the flop. So I go to the clock here. So the arrival time here is A15, right? So now they calculate like that. They calculate from 0. So the timing is that not calculate only from the clock pin, but it will calculate from the source of the clock, which is 0 picosecond here. So until the clock here is A15. Then I go through like a clock to Q. You have that like a 34 picosecond. So it becomes this. So from now, the data part, the real data part is from that Q pin and go all the way to like the input pin, the endpoint, which is with the CSN pin of the memory, right? You go here and then at the end it's here. So after that, the total time, the arrival time is 1.366 nanosecond. If you minus until here, which is like going to clock, no, it's here, clock pin here is A15, right? So you minus 1366 minus A15, you have a 51. Yep. Sorry, 5, so 3, 5. So it's a 551. Yep. 551 picosecond, right? That's the data delay. Now, oh man, what is okay. Now we go to this one. Now this one is the capture clock. This capture clock code, you see that from the beginning is also 0. But because it would take like one period, the period is 627 picosecond, right? So we add into here so that it check. So it start like the clock source latency is 0 here. But when it check the arrival time, like a requirement, it will check like it will have to add the period, right? Because remember, it capture at, let's say the first edge will be launching. So the next flop, it will be calculated at the next edge, not the same edge. Because the same edge means like you have a 0 picosecond, right? So you have to check at the next edge. The next edge is like you have to add like the period. That's a 627 picosecond is that's a period. So you start with 627 picosecond, and then you have that like here they will calculate the clock period again until like at the end go into the clock here. So it will arrive at the clock arrive in here is a 148 picosecond. Hold on, I think it. Okay. So we have a 148 picosecond. Where's that? Okay, this is 148 picosecond. However, now you have a clock reconversion pessimism. So this one is this one is the value that when you have okay, just ignore it. I think I explained that it would be too long. Just ignore this one. The clock uncertainty is here is a 53 picosecond. What is a clock uncertainty? Clock uncertainty is like this one is still like a STA, right? It will model the clock skew. As I said, you have the clock latency between the flop 1 and flop 2, right? So in that, because of the variation of voltage, variation of like parasitic cell and so on, everything. So you cannot have like the clock like whatever they calculate is correct. We have to add some margin here. That's called uncertainty. That's the margin to make sure that like so because let's say like one is at clock 1 and clock 2. Clock 1 is a 1 nanosecond, but clock 2 can be 1.1 or 1. Like or like 0.9 nanosecond, right? So in that case, we can see like the difference between that. It can be like 100 picosecond. So with that, we cannot be sure that it can happen. The clock 2 can happen anywhere from 900 to 1.1 nanosecond. So what can we do? We have to assume that like, oh, okay, now the uncertainty, we know that uncertainty is with the worst case scenario, which is like if the capture happened earlier, right? Happened earlier is the worst. So that means that we will take it as a 900 picosecond. 900 picosecond is the arrival time for the capture clock. Because if it happened like 1.1 nanosecond, then it's help, right? Because the clock will be like later, then the data part, if it like it will like include, it will increase. So that means like we have a 900 picosecond, so we have to take the worst case scenario. So that's why they will add. In this case, the uncertainty is uncertainty here. Clock uncertainty is 53 picosecond. So they have to this the conversion is at 38. Okay, so it's a minus 33 picosecond. So you have that. Then library setup time is 7 picosecond. That's this one. You guys know what it is. The setup time for the memory is a 70 picosecond. So it's minus 396. And then you have a data required time is then it required time at this one. So required time is 396, and the arrival time, I think that 1366 here. You see that is a data arrival time. Arrival time here is at 1366, but it required 1366. Yeah, it required. It arrived at 1.368. It required 396. So that means that it have a slack of 18 picosecond. It means that like it is positive. So it is arrived at 80 picosecond before the requirement, right? So this part meet the requirement. That's how I think that's how it checked. So look at that. I will send this for you, but that's how they check the setup time. When you run the synthesis and you run SDA, you look at this thing, you have to know like what is this, and then like usually you have a two way to report timing. One is you report timing without the clock, and then in that case without the clock it will show only like from here, yeah, from this part, from the clock here and go to here. That's it. And then from this part they won't show it. They will show like the clock latency go to the clock pin here. Here's the setup time. Now the whole time check, whole part will be like different. Whole part is like everything will be in the minimum, like because at the okay, the whole time you can see that. Let me see. Oh, 950. Okay, I think this one will be okay. I will explain the next time. So now I think I will need to talk with let me see who do I need to talk to? Tu and Trung, I think. Yeah, okay. All right. So I think. All right, I think we can stop here, and then like next time I will explain about the whole time. And okay, I think Tu and Trung. Okay, so you guys can drop out, and I see you next time. Thank you. By the way, you have any question? I think I will send the this thing. Okay. Let me. I will send this picture to I think I sent to Professor Then. Not yet. Okay. Hold on. Yeah, I will send these two picture. This one and the whole part here, right? You see that is a whole part. This is a setup part. So I will send this to Professor Then to upload to the BKL. And also, I think there's also like this picture. This of SDA. Yeah, this one. Yeah, those picture I will send out to you so that you can have a reference. All right. So any question? All right. All right. So you guys can drop up. So I need to talk with Tú and Bùi Văn Trung. Professor Thần, do you have anything with the teacher to talk to the teacher? Sorry, to talk to the students.
I will upload the lab material before your lab experiments next time. Okay, for the student. Yeah.
Is that I think this thing I think let me share again. Is that this thing? I think when you guys have the lab, did you see this report? Professor Thịnh, I think An Dương Gia has a question about assignment.
Sorry, which questions about?
I don't know. Can you answer that, Prof. Thịnh?
Dương Gia An, can you repeat your questions because I cannot find in the message
What
here.
assignment?
Can I speak? I want to ask that the assignment, what will we do?
About the lab experiments in next
Uh,
week.
about the assignment, because I see in the syllabus we had the score for the assignment bài tập lớn đó thầy.
No. This
Oh,
in the lab. In lab, you will have the projects, mini projects. That's mean assignment. Okay.
no assignment for no bài tập lớn for
Ah,
the theory for the class.
only in the lab.
Uh,
In the lab, you will have mini projects start from the beginning until the end. Right. I will upload the step by step in instructions about the way to do with the mini project in there. Okay, don't worry.
which tool will we work on for the lab? I think it's the Tempest, right?
Yeah.
Tempest. I think it's a Tempest thing for the cadence, because if we use cadence, it's a Tempest, which is for the STA. Do we have Tempest? Tempest.
Not a,
Okay, maybe if okay in the lab, if you guys use the I think the channels, right? Channels for the synthesis. So in channels, the built-in STA will be like have the similar format like this. It's not exactly the same, but the format will be similar. This format that I present like on the screen right now is from Synopsys. Synopsys Primetime is the standard tool for like the whole industry. When they sign up to like make the chip, they have to use this one.
yes.
Oh, okay. The channels is the cadence, and the one is like prime time is a Synopsys tool. Prime time is SDA. Channels is the Synopsys tool.
We have a tennis 19.1.
Oh, that's new. That's quite new. Not the latest, but it's still,
Yes.
yeah. I think for the purpose of the class, I think it's good. Then in the channels has the its own SA engine. Yep. Oh, okay. Yeah, those two in the lab. Okay, here I see.
Yes. I will upload the schedule for the lab, and you have 4 times 4 weeks. Yeah.
Oh, so until now the student didn't have the lab yet. They
Yeah.
didn't have any lab yet.
Not yet.
Not yet.
Next week.
Oh.
Next week. Yes.
Oh. Oh. Okay. Next week. Then. Oh man. I think so. The CC1 will miss. Okay. Whatever. I think maybe.
Don't
Yeah.
worry. I will send them the message, and then they know we know.
Yeah. No. I meant like if like if like they got the SDA here, they will like know better when they run the, because in the channel tool here, right? When they run that at the end, they will report timing. They
Yeah.
need to know what it is. It's kind of straightforward, but I think you have to you do that, and then I think if you have question, ask me. Okay, or like ask the teacher taking care of the lab.
Yeah,
They can explain to
we
you.
just around in the third week.
Sorry,
Third week,
third
not
week.
next week. Yeah, next week just about a simulation tool. Yeah.
Oh, okay. All right, good. Then I think next week I think I can introduce. Yeah, I can
Yes.
explain more
Don't
because
worry.
STA is one of the main tasks of the design STA, because doing the STA it means because at the end of the day you remember PPAS. It means a P is a performance, which is you have to make sure that the timing is met. So you need to understand how to use the STA. That's a first and foremost. All right. Anything else, everybody? All right. All right. Thank you. And then we see. And Professor, then you have anything else? If not, I think the teacher can drop off, right? Sorry, the student can drop off.
Yeah. No.
All right. Just quick one. Can you please drop off so that I can talk with the other two guys? Thank you. Goodbye, everybody. Have a good day.